Welcome to chapter 16. On this chapter, we will talk about equilibrium. Basically, the rate of the reactions being the same going forward or going backwards. So these are the things that we're going to discuss so we can understand this concept very well. First thing, just like I hinted a few seconds ago, how does equilibrium relates to reaction rates? So we're going to see what that really means. Then we're going to learn how to write the expression for the equilibrium constants. We're going to express that with the capital letter K, not for Kelvin. We're going to use it this time for equilibrium constants. And they're either going to be based on concentrations or based on pressures. And we're going to see how we can calculate one having the other by a formula that relates them. Once we get the equilibrium constant, based on the value of the constant, we have an idea of how much the products are favored or disfavored. So the formation of the products. Then we're gonna see that once we get the equilibrium constant for a reaction, we can use that equilibrium constant for any variance of that reaction. And we're going to learn how to manipulate them so we can get a value for the new reaction. And then we're going to see something that is called heterogeneous reaction. So the same way you understand homogeneous mixtures and heterogeneous mixtures, we're going to see how we do a equilibrium constant when we're dealing with a heterogeneous mixture. After we do that, then we're going to go deep into calculations. And given the equilibrium constants, we're gonna be able to calculate the equilibrium constant given concentrations. Based on the equilibrium constant and initial concentrations, we are going to be able to predict if the reaction is going to move toward the products or toward the reactants by comparing the initial concentrations to the equilibrium constant value. And then we're going to learn how to calculate equilibrium concentrations when we're given the equilibrium constant and other concentrations, like a product versus reactants or more than one reactant or something like that. And we're going to see how we're going to calculate other equilibrium constants given equilibrium concentrations given the equilibrium constant and only the beginning concentrations. And we're going to close the chapter by talking about the Le Chatelier principles that tell us when a system is in equilibrium and you do something to it, it will do whatever it needs to do to reach equilibrium once more. And we're going to see how we can predict what's going to happen based on changes to the temperature, changes to the concentrations, changes to the volume, changes to pressure, and all that. Anything that can disrupt the equilibrium. So let's begin with the definition. What does equilibrium mean in terms of a reaction? So let's say that we have a reaction, like the one I showed you before, that produces something like this. But this reaction doesn't just take the upright A and make it into an upside down A. It begins to change back and forward. So as the reaction goes to one side, immediately goes to the other side, and it never goes to completion until it reaches an equilibrium. And what does the equilibrium means? That the rate going forward from left to right is going to be equal to the rate going backwards. And we're going to express that like this. Rf equals R backwards. And we know that we can express R by the equilibrium constant times the concentration of A. That's going to be our R value to whatever power we need, right? We don't know the power until we do the experiment. And that's going to be equal to the other rate constant, but now we're going from right to left, given the concentration to that, to whatever the power happens to be once we determine. So in other words, what we're saying is equilibrium is nothing more than the relationship between two rate constants. So that's how we relate equilibrium to rates, because it's nothing more than the rate of the reaction going forward becoming equal to the rate of the reaction going backwards. We're not saying that the concentration on both sides are the same. We're only saying that the speed of transformation from reactants to products or from products to reactants is going to be equal. In other words, equilibrium. So let's talk about this one. Consider this three-step mechanism for a reaction. And we covered mechanisms back on chapter 15. Immediately you notice that this will be the step that determines the rate of the reaction or the rate expression. And we notice also that it's not the first step. So most likely, if we want to write the rate law, we're gonna have to do the steady state approximation, because the steady state approximation is based on an equilibrium. So that's how we relate those two. So which of the elementary steps represents an equilibrium? Really easy. The one that shows two arrows going back and forward. How can you represent the equilibrium using the reaction rate formula? Just basically what we just did. Rate for going forward from left to right is going to be equals to K1 times the concentration of chlorine to the first power. Why? Where is that one coming from? Remember, these are elementary steps. So the coefficients are my orders. So this is first order. And going backwards is going to be R2 from right to left, right? Equals K2 times CL to the square. Once more, this is an elementary step, so the coefficients are the order. Only when dealing with elementary steps. And an elementary step is a step on a mechanism. So we're dealing with a step number one. So how can you represent the equilibrium then? Well, we can say that K1 times chlorine to the first order is going to equals K2 times chlorine, atomic chlorine, excuse me, to the second order. So that's how we represent an equilibrium. So the equal sign kind of relates to the two arrows using the reaction rate formula. So moving to another topic. So on this topic, now that we understand what equilibrium is in relation to the rates, now we're going to talk about, so how do we write an equilibrium expression? So an expression for the equilibrium constant, excuse me, we're doing one based on the concentration and one based on the pressure, which is very related, because remember this, if we're dealing with gases, PV equals nRT. So P over RT equals MB, which is nothing more than P over RT equals molarity. So when we are dealing with pressures, we are also dealing with morality at the same time. So that's what we can talk about in terms of concentration and pressures. And we still talking about more or less the same thing. So what is the rule to write equilibrium expression? The big K. If we do it for concentration, it's going to be the concentration of the products. These are equilibrium expressions. So different from the rate law, we always use the coefficient as the power. Do not confuse one with the other. So the product or the multiplication of the products, each one elevated to its coefficient, excuse me, divided by the reactants. So that would be the Kc, or the equilibrium expression for the concentration for this reaction. So how do we do it? How do we do the Kp? Well, the Kp is going to be pressures. So we don't use the brackets anymore. Brackets denote molarity. What we're going to do is we are using pressure. So the pressure of NO to the square times the pressure of that divided over the pressure of this. Let me fix that a little bit. So it's basically a subscript to the square. So some books you're going to see it with parentheses, other books you're not going to see it with parentheses. So when you start working with this on Alex, make sure that you do it the way Alex wants you to do it. The main thing is that we're doing the pressures of each component, and we are elevating to the power of that component, which is the coefficient on the equation. So as simple as that. Products over reactants, the coefficients are the powers. So these are not orders anymore. We're not dealing with rate. So this is just the power of that expression. So here's your first daily work. So the same thing I did, just write the Kc for both of them and write the Kp for both of them. So let's do something else now. So we know how to write the equilibrium constant expression for any reaction. What about the actual value? So for this particular reaction, the molecule of iodine breaking apart into the two atoms of iodine have an equilibrium constant expression based on pressure of 6.26 10 to the minus 22. That's a extremely small number. So what this number is telling you, so I'm going to fast forward several slides. When the K constant, when the equilibrium constant is so small, it's basically telling you that this reaction barely happened. So this reaction barely happened. You will never on reality see iodine gas breaking into the atoms, at least spontaneously. And this is at room temperature. That's another thing. The same thing that happened with rates, the rate constant, they change with temperature. Remember the Arrhenius expression with the two temperatures? The same thing happened with equilibrium constants. They are unique to the specific temperatures, because if the temperature increases, then the molecules are moving faster, so you have a whole different dynamic. So what we're going to do here is see how Kp relates to Kc. And we can do that mathematically, where delta N is the difference in moles based on the coefficients between the products and the reactants for the gaseous components. So for example, on this reaction, we have 2 moles of I, which is a gas. And we're beginning with 1 mole of I2, which is a gas. So products minus reactants, 2 moles minus 1 mole, and we're only looking at the gas, equals 1. So on this case, the change in moles is going to be 1. We are given the Kp, and we are being asked to find the Kc. So that's what we're looking for. So before we go any further, let's go ahead and do some algebra here, and let's solve for the Kc. So Kp over RT to the 1, we saw that the delta n is going to be 1, equals Kc. So that's what we do. We take this formula and we transform it using the lovely math that we know into that one. So this is the formula that we are going to be using. So let me clear the screen a little bit. So what numbers do we need to plug in there? Well, we know our Kp, right? Kp is 6.26 10 to the minus 22. By the way, equilibrium constant do not have units, and the reason is based on the activity, and that's a lecture by itself. So believe this by faith. It's based on the activity. Because of the activity, there's no units. The books give you like 1 or 2 sentences that is not enough to understand why. So Kp is going to be that. We're going to divide it by the temperature, 298 Kelvin. And then we have R. So R can be this value, or it could be this value. Which one do you think we need to be dealing with? We're dealing with Kp, which is based on pressure. So we're not using the energy. We're using the one that contains unit of pressure. So 0.08205 821 liters times atmosphere moles Kelvin. As you can see, Kelvin is going to cancel with Kelvin. But however, we're looking for a Kc, and I already told you there's no units. So don't try to cancel the units because you're not gonna be able to. Just remember, there's no units on the equilibrium constants. So we know we have to use the temperature in Kelvin. You know the value of the R that you need, the one that involves pressure, and then you just have the Kp on top. And then you just put it on the calculator and you get your answer. So that's how we use the formula. So there's a way to connect the Kc to the Kp, and this is the formula that you need. And you can solve for Kc if Kp is given. So with that said, this is your daily work. So you're giving Kp, so you're looking for Kc. And here's your other daily work. You're giving Kc, so you're looking for Kp. So you get to practice both of them. So a new concept. How can we relate the magnitude of an equilibrium constant to the relative amount of reactants and products? What does that mean? What if I get a equilibrium constant that is bigger? And I'm not talking just bigger, I'm talking a lot bigger than 1. Well, let's think about it. The K is the concentration of the products over the concentration of the reactants. If this is bigger than 1, then that means the product is the bigger one. Pure, right? For that to be bigger than 1, the numerator has to be the biggest one. And what is the numerator? Like I said before, it's always products over reactants. So if you get a number, equilibrium constant bigger than 1, that means the products predominate. The numerator is the bigger number. If you get a k that is a lot smaller than 1, like the one like this one here, for example. Well, this one is to the minus 3. That's not a lot smaller. So you gotta kind of think about that. This one is huge. That one is a lot bigger than 1. So the product definitely predominates on that one. So if you get a k that is a lot smaller than 1, the only way you get that is because the reactants or the denominator is the bigger number. That's the only way you're going to get a number less than 1. And that's it. So a very simple concept, but super important. So now you have enough information to work on this daily work. A quick overview of this. You have a balance equation, which is on equilibrium, so you should be able to write a K. Since we have brackets, it's going to be Kc. So you're gonna be able to write it. Product over reactant based on everything I told you. So if the concentrations are given, you should be able to find the Kc. If the Kc is given, you should be able to find the unknown. So if you can do that, then you know exactly how to write an equilibrium expression. And once you find your case, tell me which of them, the one at 500 or the one at 575, is the one that favored the products the most. And you know how to do that based on what we talk about the magnitude of the equilibrium constant. And that's it. There's not much more to say there. And with that said, we come to the first section. So next time we come around, we're going to talk more about the equilibrium constant, but we're going to be able to start manipulating it. Knowing a reaction, can we manipulate it for any reaction that relates to that reaction? So that's what we're doing next time. So let's leave it there for right now. If you need more information, watch the recording again, watch the tutorial videos on Canvas, go to the textbook and see the problems done step by step, or come to the Science Learning Center to my office or to the 24/7 tutor service that we have. So until next, see you later. Take care.